Here's the plan. We are building a secure network server using pure Rust code. Here, we will not just testing it locally. Your actual phone counts as a real client today. Connect 4 devices at once. One async Rust process easily handles all the incoming traffic. You could choose to write this entire network project using just C or C++. But we actually want to sleep safely tonight, so we are absolutely not doing that. 600 lines of Rust code, full TLS encryption, 0 frameworks. Let us begin now. Let us run the exact same problem in all three. Watch the memory layout closely. C frees a memory block but keeps the pointer. Everything fails completely and utterly silent. C++ double frees the exact same block. This is also totally fine apparently. But if Rust tries to pull the exact same trick, it does not even compile successfully. The border checker steps in. You catch bug at your desk, not in the production outage. Fix the lifetime and quickly move on. C and C++ holds life grenades. Let us actively raise them. 4 languages, 1 fatal memory bug. Who catches it first? Rust dies at the compiler. Java survives until your test suite finally catches the error. C++ might check fault later. C just waits for users to report the bug. Now for the classic objection. All this memory safety must completely ruin your runtime performance. It actually does not. The check happens entirely at compile time. At runtime, absolutely nothing. You get the bare metal speed all the time, but you decide when bugs actually show up safely. Here is the full architectural blueprint mapped just once before we write the Rust code. It all starts right at the client, your phone hitting a specific network API route. It actually just sends raw text, a method, a path and a body, no magic. Over plain HTTP, the text file out over the network exactly as it was written. Wi-Fi is a shared medium. Anyone running Wireshark can easily read your plain text request. Now wrap it up in TLS and that request becomes pure cryptographic noise to everyone listening locally. It hits your laptop at a port, basically a numbered operating system network access door. It binds to a loopback and only local processes can knock. Your external phone instantly times out. Binding to 0.0.0.0 literally listens to everything everywhere constantly. None of this works until both sides formally agree on how to encrypt these connections. The client sends a list. Here are the cryptographic cipher suites I can speak smoothly. The server picks its favorite. Both sides now know exactly how the complex math works. Then the server sends its certificate. This is where most developers get stuck very quickly. It is 3 things stapled together: a public key, a name list and a signature. The client checks that list carefully against the IP address you actually typed in earlier. Hit an address that the certificate does not recognize and it refuses the connection absolutely outright. Match the exact address perfectly and the connection securely carries on without a single hitch. That single tiny check explains 90% of the completely broken local software testing environments. Now the keys. Both sides invent a completely random secret and keeps it stored locally. They swap the public halves out in the open. Anyone listening actively just grabs them. Mathematically, if they derive the exact same shared key, it is never successfully intercepted by hackers. Both sides finally say finished and complex TLS handshake protocol is formally officially complete. The channel is now fully private. That green browser padlock symbol actually means something real. Only after all that negotiations does the first actual byte of HTTP data safely move. Inside the Rust process, we only have 3 moving parts to worry about right now. Rust ls strips the encryption entirely. After that, we just safely use plain standard Rust structs. The router compares the incoming path strictly against our table and correctly finds the match. The handler securely runs and successfully inserts one new row, that is the right path. A 201 response goes back, getting encrypted securely exactly as it leaves us. And your phone instantly redraws the screen, one complete secure round trip end to end. Before we look at the code, here's the structure. One master cargo workspace project directory. 4 distinct crates inside it and each one has exactly one highly isolated specific job. Both server and client completely depends on the protocol crate. This is our secret weapon. The protocol crate securely holds core data types and critical validation functions for both. The search crate handles certification generation and cleanly discovers your local IP dynamically. The server crate handles boot up sequence, API routing and serving HTML pages. Here's why we explicitly split them. The data type is safely defined exactly once. Rename a field on the server and the client instantly stops compiling completely and utterly. It is annoying for 5 seconds but prevents terrible silent API mismatches in production environments. We are now going to read the exactly 5 files strictly in this extremely specific order. Identify securely first, then the server engine, then the exact specific shape of our data. The Rust code will be strictly on the left and the physical visuals mechanics on the right. File 1. Exactly 12 lines that generate a custom TLS certificate from nothing. First, a highly secured key pair, the private half of it never leaves your machine. Then the acceptable names. This is the list your phone will verify against very shortly. Then it formally signs itself. This is the only difference from a real public site. Real sites pay external authorities to watch for them, we just cheaply watch for ourselves. Your phone throws a security warning, the encryption is identical but absolute trust fails. Which exact address goes in the cert? Your operating system actually has few available. Loopback is totally useless to the phone. Same with your messy local talker network breaches. Our VPN would annoyingly steal priorities, so we rank them and explicitly pick Wi-Fi. File 2. The secure server boot sequence is precisely 3 steps and about 20 lines. First, we need to carefully choose the underlying cryptography engine. We go strongly with Ring. Rust LS refuses to guess your backend, so you must compile it in explicitly. Second, we must secure load the certificate and the private key directly from the local disk. They are strictly verified against each other immediately. They absolutely must be a perfect match. Give it a totally mismatched key and it crashes cleanly right at the initial server startup. Third, we desperately need a listening address. Your machine actually has multiple network hardware interface. Listening on 0.0.0.0 successfully open all local network interfaces. Bind directly to loopback instead and your incoming phone packets will unfortunately just bounce off. Then bind Rust LS. It securely wraps the socket, the handshake and HTTP traffic together nicely. Every connection negotiates encryption before the router sees a single byte. It does this concurrently for every request, and this is the server. Moving on to file 3, the API routes perfectly fit into 4 rows. The root / correctly return HTML pages, the rest handles the JSON API. A web request safely comes in, hit matching rows and fires the handlers. The include string macro successfully embeds HTML pages directly into the compiled binary. You securely deploy one single executable. There is no front-end folder to delete. Read it from disk instead and you literally beg for production file errors. Next up is the data store. Write it naively, it looks perfectly fine. But Axiom framework clones states per request. Every clone gets its isolated list. Save an item right here and it goes missing there. Data ghosts you. Luckily, it does not actually compile. The strict compiler correctly blocks this code. It tells you exactly why immediately standard vectors cannot be shared across threads. What you actually truly want is one master list that every other thread shares. Arc does exactly that perfectly. Many owners can safely share one single value. Mutex is the vital other half. One writer completely prevents any data corruption. Add an item securely just once and every single clone properly sees it. Let us safely look at one complete handler. Request bodies naturally arrives raw. The types try passing it. Garbage JSON gets securely rejected before running anything. We then validate fields. Empty names instantly trigger bad request error response. File number 4 is deceptively tiny but permanently eliminates massive backend bug classes. The core data shape gets explicitly compiled into both programs from scratch directly. Add a completely new field and both binaries securely stop compiling until fixed. File 5. The network client. There is one extremely lazy and dangerous line. Trusting any certificate means malicious middlemen perfectly answer your incoming network traffic requests. The green padlock still shows up, pointing strictly at dangerous attacker machine. The absolute secure fix is one simple line: we trust only our certificate. Now a completely forced network certificate immediately pawns off our secure Rust client. So does the flawless real one from Google. We formally lock internal backends. Does it really hold up? 4 connected clients basically failed any load tests. 50 is much better indeed. Notice each connection cleanly uses lightweight async tasks. Spawning real heavy OS threads would unfortunately burn hundreds of megabytes just idling. There are exactly 2 honest bottlenecks here. Every write safely queues behind mutexes. Deleting requires inefficiently scanning the whole list, terrible for a million data rows. Both are completely deliberate bottlenecks. Building those performance fixes is the next project. 3 specific things this server absolutely strictly avoids because I am completely upfront. No database persistence, no user accounts, no rate limits, all are intentionally skipped. What you have cleanly left is real TLS, shared types and fast backends. That is the complete network architecture path, entirely mapped out and safely built. Exactly 3 simple terminal commands safely get you a fully running secure system. A client, a server and raw pure Rust running securely right in between. If you like the content and this project, there are many more to come. Share this with your friends and subscribe to BareMetal.